Hello again. This is video lecture 33.1, and we will be discussing section 1 in chapter 33. The chapter is entitled Electromagnetic Waves. Now, we studied waves earlier in the year, as I mentioned at the end of a previous class, but there we studied what were called mechanical waves, such as a wave on a string being moved up and down, or sound wave, where parcels of air oscillate. Or sound waves in water. But those are all mechanical waves where you have to have what's called a medium, a material, for the disturbance, the wave, to travel through. We are now going to learn about a completely different kind of wave. It's still a wave in the sense that there's something or some things that are oscillating in space and time, and that you can have a sinusoidal wave version of it, where the things that oscillating is a sinusoidal function of space and time. We studied that earlier in mechanical waves. But the thing that's oscillating now is the electromagnetic field, which consists of an electric wave and a magnetic wave. And that tends to have some rather specific properties different than, say, a wave on a string or a sound wave in air. And yet electromagnetic waves are one of the most important entities for technology that we have. Just think about everything that you need that's related to your cell phone, because that's all based on electromagnetic waves. Okay? All right, but we got to build up some understanding first. So in this chapter, section 1 on electromagnetic waves, let me get us started. First, let me remind you, we have been studying what's called electromagnetism, the study of electric and magnetic fields, which culminates in the writing of the 4 Maxwell equations that describe the behavior of electric and magnetic fields. We're now segging into a field in physics that is called optics, which historically means the study of what we call light. And when we as humans say the word light, we mean that which we see with our eyes. But what Maxwell showed us is that light, the thing that we see with our eyes, and that people studied for many years, including Newton, for example, in the 1600s. Light is just an example of an oscillating electric and magnetic field in the visible region of what we call the electromagnetic spectrum. That's where we're headed. But first, let me show you, I'm going to have to expand this picture a little bit so you can see it better. Let me show you a way, very practical way in some sense, that you can actually produce an electromagnetic wave. It's basically the way any kind of radio transmission tower works to produce electromagnetic waves in the radio region of the spectrum. We have a very simple schematic circuit diagram on the left. We need some kind of energy source that's supplying energy. The main circuit is called an RLC circuit because it consists of a resistor, an inductor, and a capacitor. And we had to omit chapter 31 in our study because of time factors, but chapter 31 is all about circuits like that. Circuits with R and L and C, or even circuits with just L and C. And what you discover in a circuit with an inductor and a capacitor is that the current and the voltage in it oscillate with time. You have what's called an AC circuit. And so with an RLC circuit, you also have oscillations. The current and the voltage oscillate with time. And that's what that circuit will do. This thing called a transformer just gives you a boost in voltage and a transmission line to an electric dipole antenna, which is usually going to be of the order of a meter to many meters in size. And what you end up having is an AC current that oscillates up and down in that antenna. And it oscillates up and down at a frequency f determined by the L and the C. And that frequency is this, f equals 2 pi over root LC. And the oscillating current up and down in the dipole antenna means, say, electrons are accelerating up and down and up and down. You get an electromagnetic wave. Okay? You have to have accelerating charge. And so these arcs that you see in the diagram are a very schematic way of representing what are called wave fronts for this traveling electromagnetic wave as it travels outward from the antenna. And as you can see, the farther you get from the antenna, the source, the more flat these wave fronts become, more planar, like the palm of your hand, as opposed to curved. And we're going to look mostly, we would be studying electromagnetic waves that are quite distant from their source. And so their wave fronts are flat or planar. And you have what are called planar electromagnetic waves. The mathematics is just a little easier to deal with. Okay, that's a way you can make an electromagnetic wave. Now, I want to imagine that we have planted ourselves, so to speak, at some distant point, really even farther than this, but some distant point P from our antenna, our source. And I want to draw a schematic picture of what the actual electric part of the electromagnetic wave and the magnetic part of the electromagnetic wave, how they behave with time. So what I have here is a series of pictures. We're going to have to talk our way through it at this distant point P. And we are standing at that distant point P. Let me go back here a minute. And we are looking back, that's our eye. We're looking back towards the source, the antenna. So if you like, that wavefront is coming straight towards us. That's our perspective. Okay, I'm going to start at the point P as represented at the top of this diagram. We have at this moment in time, at point P, we have the greatest magnitude fields. The electric field points in the plus Y direction. The magnetic field points in the plus Z for this planar electromagnetic wave. I'm just telling you what we observe. Then, a little bit later in time, follow the arrow here. Same point P in space, just stay put, but wait a little bit of time. The electric field still points in plus Y, but it's a little bit smaller. The magnetic field still points in plus Z, but it's a little bit smaller. Again, wait a little bit more in time, still stay at the point P. No fields at all. 1 instant in time. Wait a little bit longer, and now the electric field points in negative Y, but it's not very big. And the magnetic field points in negative Z, but it's not very big. Wait a little bit longer still. Now the electric field has its greatest downward magnitude in negative Y. And the magnetic field has its greatest magnitude in negative Z. Now wait a little bit longer. And E is downward but small, and B is to the right but small. And wait a little bit longer. Now there's no fields at all at that moment. And wait a little bit longer. Now E is small but pointing up, and B is small but pointing to the left. And wait a little bit longer, and you're back where you started, and it just goes around again. We have oscillating electric and magnetic fields. But they're oscillating in very specific ways that I want to emphasize. Okay? And I'm supposing that this wave is traveling right towards us, and towards us in this picture is outward from the screen. Okay? All right, and the wave is traveling towards us. So the wave is traveling in this scenario in the plus X direction. Then here's one thing I immediately observe. Both the electric field E and the magnetic field B are always perpendicular to the direction in which the wave is traveling. You see that? If the wave's traveling towards us in the plus X direction, the electric field is always oscillating parallel to Y, and the magnetic field is always oscillating parallel to Z. So both E and B oscillate perpendicular to the direction the wave is traveling. Aha! That means the electromagnetic wave is called a transverse wave. We studied that in chapter 16, transverse waves on a string. Here's another observation. The electric field E and the magnetic field B are always perpendicular to each other. Picture clearly shows that. One more observation. The electric field E and the magnetic field B are always in phase with each other. When one is a maximum, the other is a maximum. When one is zero, the other is zero. These are all things we're just observing from this little diagram about electromagnetic waves. Okay. All right, now what I want to do is I want to go to animations where we can have things changing with time and look at some electromagnetic waves in an animation. So I need to go to Wiley Plus. And what we're seeing here, once I run it, we will see electric and magnetic fields oscillating at various places in two planes. The plane shaded in blue is at x equals 0. It's the YZ plane. And the plane shaded in green is parallel to the first one, but displaced a bit along the x-axis. It happens to be a distance d of 2.5 centimeters, but that's okay. And it's going to depict both the E and the B vectors at 9 different locations in each plane, and we're going to watch them as time goes on. Okay, so that's what we're going to do. I'm just going to run it for now, the animation. I'll probably pause it as we go. Okay, so we see oscillations of E and B. Let me pause it for a moment. The dark reddish arrows that are oscillating parallel to Y are electric field vectors. The dark green arrows that are oscillating parallel to Z are magnetic field vectors. And here's one thing that's very useful to remember. And we can actually see it. Go back for just a second. If I go back to my slides, from the picture right up above, if plus x is out of the screen, and let's focus on, let's say, that picture right there, the directions of the E and the B, I will just point out that from the right-hand rule, the direction of E cross B is the direction of the wave travel. Do the right-hand rule. Cross E on top of B. E points in the plus Y. B points in the plus Z. Your thumb points straight out towards you. That's plus X. That's a handy thing to remember. The direction of E cross B is the direction the wave is traveling in. Note then back in the animation, say at this moment, all right, that you could do E cross B, the E's being the kind of dark red arrows, the B being the dark green arrows, and figure out the direction the wave is traveling in this particular animation. Okay? All right, but I just want to run this some more so that you can see the oscillating electric and magnetic field vectors in 2 different planes. Okay, and you could see that, I'll run it some more. For the spacing of those 2 planes, the E and the B field vectors, they don't agree with each other in the 2 planes. They don't have to. But no matter which plane you look at, the E oscillates perpendicular to X. The B oscillates perpendicular to X. The E and B are perpendicular to each other. At any given instant, the E and B are in phase. When one's a max, the other's a max, etc. Okay? That's what's going on, and it's a lot, I know. Let me look at this animation next. Okay? Now, here what we're going to do is we're going to take just the electric field part and draw it just for a series of points on the x-axis, but distributed along the x-axis. And so at this moment in time where we've said freeze, you can see the electric field vectors. And they, in fact, form, in this case, a sinusoidal wave, right? It's a sinusoidal curve. And then there's a wavefront, which happens to be at a location where the electric field is a maximum. And when I run the animation, that wavefront's going to travel in the direction of the red arrow. Let's watch. So that shows the oscillations of the electric fields at different points right on the x-axis as a function of time. And the electric field's oscillating parallel to the y direction. Now there's the magnetic field part. It's oscillating parallel to z. And we can watch that plane wave front move for that wave. Okay? And then we can put them both together. E and B. It gets a bit busy, but that's what's happening. Notice that distance between two peaks along the electric wave part is called a wavelength, lambda. And that whole structure is traveling to the right, plus x. And at any given time, E cross B, as given by the right-hand rule, points in plus x, the direction the wave is traveling. It's that kind of wave that we are interested in. Okay? This would be called a sinusoidal electromagnetic plane wave. Now let me go back to my notes. All right, so now let me focus on the mathematical properties of an electromagnetic wave. All right, so what is an electromagnetic wave? It is coupled, transverse, electric and magnetic waves, as we've shown in the animations, that move in vacuum at a certain speed. In vacuum is important when you study electromagnetic waves. That means empty space. A vacuum is completely empty. And the very well-known speed at which these electromagnetic waves travel, measured even before the time of Maxwell, although not with the level of precision you see here, is given with this famous symbol, little c. That is the very well-known symbol for the speed of an electromagnetic wave in vacuum. And the number has been measured now so precisely that the speed of light is defined to be the following number: 299,792,458 meters per second. I say again, 299,792,458 meters per second. Now, that's pretty fast, isn't it? What most textbooks will do will round that and write it in scientific notation, like this: 3 times 10 to the 8 meters per second. 3.00 times 10 to the 8 meters per second. All right, let's suppose that we have an electromagnetic wave traveling in the plus x direction, with the electric field oscillating parallel to the y-axis, the magnetic field oscillating parallel to the z-axis. And we're also going to assume that at time 0 and at the origin, both fields are 0. What is then the equation of such a sinusoidal electromagnetic wave? It's both of these formulas right here. Because they're sinusoidal, traveling waves, traveling in the plus x direction, the wave function that describes them has the generic form that we studied in chapter 16. Sine of kx minus omega t. We use that very same formula to study sinusoidal waves on a string. Sinusoidal traveling waves on a string. And now what we have are sinusoidal traveling electromagnetic waves. The number out front of each is the amplitude of it, which is the maximum displacement or the maximum value of it. So in the electric field part, that's called E max, the amplitude of the electric wave part. And for the magnetic field part, that amplitude's called B max. And those are the maximum values, respectively, for E, that would be newtons per coulomb, or volts per meter, and B, in Tesla. Note, when the argument is kx minus omega t, that means it's a traveling wave, traveling in the plus x direction. And the symbol omega is called the angular frequency of the wave. It's equal to 2 pi f, where f is the regular frequency, in the unit called hertz. It can also be written, that omega, as 2 pi over the period, capital T, in seconds. And the unit of angular frequency is radian per second. The symbol k is called the angular wave number, which is 2 pi over the repeat distance of the wave, lambda, which is called the wavelength of the wave, and the angular wave number k is in radians per meter. I'm doing that fast because we did that in chapter 16. And the speed of the wave, which, since we're talking about an electromagnetic wave in vacuum, would be labeled by a c, not a v, is given by the angular frequency omega divided by the angular wave number k, and that puts it in meters per second. So all of that is going to be applicable here. Now I want to show you one more thing about these two waves and what we can learn about them together. This is what Maxwell did for the first time. Using Faraday's law, which of course Maxwell would have known and understood very well, you can show that for this wave, the following two partial derivatives must be equal. Remember, partial derivative. The partial of the electric field with respect to the x-coordinate must equal the negative of the partial derivative of the magnetic field with respect to the t variable, where we're using those expressions for the E and the B. So let's do those partial derivatives real fast, okay? What is the partial of E with respect to x? That means take the derivative of the function E with respect to x and treat t as a constant. You got to use the chain rule because I've got sine of blob, where blob is kx minus omega t. When I take the derivative of sine blob, I get cosine blob times the derivative of the blob. Again, the blob is kx minus omega t. The derivative of that with respect to x is just k. So what we get is k times E max times cosine blob, cosine kx minus omega t. And then I need the partial derivative of b with respect to t. So now I go to the b function, I take the partial of it with respect to t. So it's still sine blob. The derivative of sine blob is cosine blob times the derivative of the blob. But now I'm differentiating with respect to t, so the derivative of that is just a negative omega. So this is going to become minus omega b max cosine blob. And I put both those expressions into that. Let's see what we get. I'll write it right beneath here. K E max cosine of kx minus omega t equals negative omega b max cosine omega t. I got two negatives multiplied together, so the negatives cancel. Those two sides must be equal for all values of x and t, all values of x and t. So that means we require the things out front of the cosine on each side must be equal. So k times E max must equal omega times B max. Or E max over B max, just cross multiply, equals omega over k. And that's what I've got written right here. That's the ratio of the amplitudes of the two waves, the electric wave amplitude, E max, and the magnetic field, the magnetic wave amplitude, B max. And that ratio is now, I've learned, fixed. It's equal to the ratio of the angular frequency of the waves, omega, to the angular wave number, k. But that ratio is equal to the speed of the wave, little c. So that's a very important relationship. Emax over Bmax is equal to c. All right, so I used all that. Now let me use another idea. Using Maxwell's law of induction, which we just talked about in chapter 32, you can show that another partial derivative relationship has to be true, right here. The partial derivative of b with respect to x must equal negative mu0 times epsilon 0, partial derivative of e with respect to t. And note the presence of both the magnetic constant and the electric constant. So you do those partials, partial of b with respect to x, partial of e with respect to t, and you get the next line. This is the partial of b with respect to x right there. And this right here is the partial of e with respect to t. Need to make sure you can see that. Those two sides must be equal for all values of x and t. So the stuff out front for each one must be the same. Okay? So that would be, I'll write it over here to the side because there's something else that has happened. Kb max must equal mu0, epsilon 0, omega times Emax. But then we'll substitute what we just learned, that the ratio of the wave amplitudes equals c. Emax over Bmax equals c. Or rearranging, Bmax equals Emax over c. And then we get this expression. K Emax over c equals mu0 epsilon 0 omega Emax. Cancel the factors of Emax. Take the c over to the other side. K equals mu0 epsilon 0 omega times c. Next, divide both sides by k. 1 equals mu0 epsilon 0 c omega over k. But omega over k, that combination, equals c. So now what I've got is 1 equals mu0 epsilon 0 c squared. I'm being very careful about how I reveal these things. So solve that equation for c. c equals 1 over the square root of mu0 epsilon 0. Interesting. The speed at which these electromagnetic waves travel through vacuum is determined by those two constants, the magnetic constant and the electric constant. And we have values for those, right? Epsilon 0 is 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. And mu 0 is 4 pi times 10 to the negative 7 Tesla meter over ampere. So you ought to try this. I really recommend you do. Pause the video is fine, but you go to your calculator and you take that number, 8.85 times 10 to the minus 12, times that number, 4 pi times 10 to the minus 7, multiply them, right? Take the square root, and then take 1 over x and see what you get. I'm now going to tell you. You get 3 times 10 to the 8 to 2 sig figs. 3 times 10 to the 8. And yes, the unit would be meter per second because it's got to be the speed of the wave. But look what the number is. The well-known value for the speed of light. I want to emphasize how important this result is. Imagine James Clerk Maxwell in the 1850s or so, roughly, doing these calculations for the first time. Everybody at that time knew about light, of course, and they even knew that the speed of light had been measured in experiments, difficult ones, because the speed is so fast, but they did it. And they knew that it was 3 times 10 to the 8 meters per second. So imagine Maxwell's, I can only try to imagine, his shock, amazement, thrill at discovering that, first of all, there can be such a thing as an electromagnetic wave. And then when he calculated the speed at which those electromagnetic waves travel, he got the number that was already known to be the speed of light. So guess what light is? It's a traveling electromagnetic wave. Nobody up to that point in human history, that at least we're aware of, from the publications, knew that. Now maybe there were some people who knew that before, but it never got into any written records. So we have to give credit to Maxwell as being the first human to realize what light is. A traveling electromagnetic wave. Furthermore, his calculations show that electromagnetic waves can have any wavelength whatsoever. That's the lambda, remember? Any wavelength whatsoever. And that all electromagnetic waves travel at speed c, this speed, in vacuum. And that the visible region of what we now call the electromagnetic spectrum is the part that our eyes have evolved to be sensitive to, right? Our eyes, human eyes. And that wavelength range is roughly 400 nanometers at the small side to 700 nanometers at the big side, big end. So again, what he's discovered is, okay, light is an oscillating electromagnetic wave. We know roughly the wavelength of it for the part that we can see, 400 to 700 nanometers. But you can have any wavelength, electromagnetic wave. So there must be electromagnetic wavelengths for waves that are not something that we can see with our eyes. And so what we opened up at that point is what has sometimes been called, poetically, Maxwell's rainbow. And here what we have is like two number lines or number axes on a logarithmic scale. Every tick marks a power of 10. The upper one is the wavelength in meters, and the lower one is the frequency in hertz, with wavelength increasing to the left and frequency increasing to the right. And it has no real end at either side. And what Maxwell did was open up that entire spectrum. You can have an electromagnetic wave of any wavelength or any frequency. And only over this very narrow range where you see the rainbow, between about 400 and 700 nanometers, here's the expanded view of it, is the visible part of the spectrum for us. At the long wavelength end, you have red light. At the short wavelength of the visible spectrum end, 400 nanometers, you have violet light. And you get the different colors in between. But Maxwell then pointed out all these other possible wavelengths and frequencies, which people then promptly went out and tried to figure out ways to detect. And Hertz was one of the first to detect electromagnetic waves outside the visible spectrum. Okay? But now we use long wavelength, radio waves, infrared, ultraviolet, X-rays. I mean, we use them all in technological applications. All of that was opened up. We have even made the electromagnetic spectrum into a commodity. Yes? You can buy regions of the electromagnetic spectrum to broadcast on if you want to, say, broadcast television or radio. You can buy regions of the spectrum. So, of course, we've monetized it. But just think of the applications that use these other wavelengths. Maxwell pointed out the existence of all this. Okay? All right, now we'll just close with a class engagement exercise. On Blackboard. With electromagnetic waves, practice with electromagnetic waves. Here's the first question. The figure below shows the electric and magnetic fields of an electromagnetic wave at a certain instant. One simple question. Is the wave traveling into the page, away from us, or out of the page or screen, towards us? That's question 1. Here's question 2. Suppose the magnetic field part of a light wave oscillates parallel to a y-axis and is given by that formula. B sub y, because it's a y component, is B max sine of kz minus omega t. First question, A. In what direction does the wave travel? And B. Parallel to which axis does the associated electric field oscillate? Okay, so that's our introduction to sinusoidal electromagnetic waves. I'm going to do something a little bit differently in class on Monday. I'm going to not focus on this content. So this video lecture is what you get for it. You can also read, of course, in the book, Chapter 33, Section 1 on Wiley Plus. But class on Monday is going to be going to the next section. Okay? Just to give you a heads up, it'll be a little bit different in Monday's class. But this is our first lecture on Chapter 33, and that's all we're going to do for right now.